Hi, this is Tim, testing video. Up, down, right, and left, and audio. Okay guys, we're going to pick up around page 45 in the book. We have done the nearest neighbor algorithm, which is a local and greedy. We've done the sorted edge algorithm, which is global and greedy. Let's just see how this applies. So here's a list of a very large complete graph, A, B, C, D, E, F. And I'd like to run the algorithm, nearest neighbor and sorted edge. So first I'm going to do the nearest neighbor. And I'm going to start at F. Now why in the world do I want to start at F? Well, maybe the guy lives at F. It is what it is. So if we look at the graph and we say F, what is closest to F? Well, you read this whole list and, C is closest to F at a cost of 11. All you had to do was look either the F column or the F row or the F column. Now, we're at C. C to F is 11. We've already been there. So now we have to choose between 14 and 15. Well, that means 14 is what we pick because it's smaller, but which one should we do? C to D or C to A? Well, either is correct. The algorithm doesn't give you a unique answer, so there's actually two fundamentally correct answers to this nearest neighbor algorithm. I'm going to do C to A. Now I'm at A, and the smallest number for A to go to is B for 9. Now I'm at B, and the smallest number 9, but that's where I am at. B to A, I've already been there. Two 15s. I've already been to C, can't do that. So I have to go to D. That's a cost of 15. And I want you to notice at this point, we're kind of forced at the end. What has happened is we've covered all of the vertices A, B, C, D. We've only missed E, so D has to go to E. This is forced. D to E, which is 12, even though it is the smallest one, and E to F to complete your circuit, E to F, which is 13. And this is a very nice nearest neighbor algorithm. And we didn't have to create the gross big graph. Now, we could also write it as if we were someplace else. For example, write the circuit as if it started at D. Well, it still was the nearest neighbor algorithm started at F to produce the answer, but I could write it as D in two ways. I could say D, E, F, C, A, B, D, or I could run it backwards. I could write it as D, B, A, C, F, E, D. Both of these are legitimate ways to write this answer, but one would, if you wanted to say where it came from, you would say it's a nearest neighbor algorithm started at F, listed from D. All right, so now I'm going to take this same piece of information in this table, and I'm going to do the sorted edge algorithm as well as like I did before without drawing the graph. So the sorted edge algorithm, I simply look at this entire graph and I say, what is closest? So I'm going to write down my vertices in some order, and then I'm just going to put the edges in as they get picked. So A to B is 9. That is the smallest number. So I put that in. I'm not at A. I'm not at B. I just say sometime in the future I will drive A to B or B to A. The next smallest number is 11, so I'm going to fill in CF for 11. Now that clearly points out that we're not anywhere in particular. We're just picking that path that will create a circuit when done. Now the next smallest number after 11 is 12. Is there just one 12? Yep, and that's the DE. And boy, it starts like we really don't have a circuit at all here. It's 3 separate edges. We're just saying at some time we're going to drive those. Now comes 13. Oh, there's 2 13. Should I pick AD or should I pick EF? Actually, I think I can pick both. So I'm going to put in AD for 13. And I'm going to put in EF for 13. And just like that, I've got a circuit made. And what's going to happen is now the last edge is forced on us. And that's BC for 14. And so there's the sorted edge algorithm. It didn't start anywhere. It simply comes into fruition. And you can write down the answer: A, B, C, F, E, D, A. Now, it's possible that's the same answer we got before. Probably not. Let's take a look. Did I do an A something before? No, I never wrote it as if it started at A. Let's see. The other one was A, B, D, E, F, C, A. That's not the same one that goes AB. It goes ABD, this one goes ABC. We got a different answer. So the nearest neighbor and sorted edge produced 2 different answers. They could have produced the same. They both are algorithms. One is probably better than the other. Neither of these are thought or known to be optimal. It's just what happens. Now, we're going to do another problem that is very similar to what we've been just doing, but it involves a very special concept called a tree. Now, trees are unique pictures. That's a tree. How do I know it's a tree? Well, first off, there's not a circuit to be found no matter how I try. There's a couple of characteristics that trees have. The first characteristic, if you count the vertices, so let's count the vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 vertices. And now we count the edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. It's always the case that the vertices are greater than the edges by 1 in any tree that you draw. The second interesting characteristic is that there's actually one path from any vertex, say I, to vertex J. So if here's, let's say, vertex 3, we name it, and here is vertex 7. There's only one way to get there quickly without repeating anything. I mean, we could do this 9 times and up and over. But if we're talking going straight there, that is the only way to get there. There's one path between any 2 vertices. It's connected. It's only one piece to it. If I added a second graph, let's say this officially was the graph, like let's say it's the map of Maui and Oahu. They're not connected. That's a tree, this is a tree, but the graph together isn't a tree because it actually doesn't have this property anymore. We have a fancy name when you have more than one tree. We call it a forest or a woods. But we pretty much always like to work with connected graphs. The last thing is there's actually the idea of maintaining connection by an edge. Every edge is required for maintaining connection. So notice, if I were to cross out this edge, the graph would break into two pieces. If I were to cross out this edge, the graph would break into two pieces. That's another property of a tree. Some people refer to this as that every edge is a bridge. I don't really like that terminology, but some people do use it. This is a tree. Now, what's nice about trees is they actually represent what we frequently do with utilities. We have a water tower, and it distributes water to all the city mains, and then at the very end, a bunch of houses are connected. And it looks like a tree. We don't let the water circulate. One of the reasons is I don't want the water to go into your house and then go into mine. You could mess with my water. Security. Here's another application, the sewage system. Your houses are connected to a sewage system that goes in one and then continues out. We really don't want, again, your sewage running through my house before it goes in the sewer. Same thing with electricity. Although we have a line in and out often, the pair of lines looks like this. We don't want to create loops because that creates a short in the system. So in other words, it seems that there's a ton of things like utilities that use trees. So I'm going to do a problem that's actually kind of a famous problem. I'm going to draw a non-complete graph with weighted edges. There it is. And now I'm going to weight the edges 6, 5, 4, 3, 5, 4, 6, 5, 3, 2, 7, 4, 3, 6, 5. Now, the problem I'm going to do is the following. Suppose this tree, this graph right here, represents the possible ways to build the water lines in a new built community. And the numbers on the edge represent cost. So if we have the weights represent cost, the edges represents to be built / used, and we want a tree to connect everything. We don't want every edge to be used. Well, it turns out there's a very efficient algorithm for this to create a tree, and the algorithm is almost the sorted edge algorithm, and it's really simple. What it says is pick the least, highlight it. Pick the least, highlight it. Pick the least, highlight it. So it's a repeat of least, highlight, repeat, with one caveat, except never a circuit. So it's got one little exception. So I'm going to do this one here. I'm going to pick the 2, highlight it. Now, there are several 3s. I'm going to highlight them. Make sure when I highlight them, I get no circuit. Notice I don't have a tree at the moment, but it's building. Now I'm going to pick the next numbers 4. So I'm going to highlight this. Highlight this. Now I can't highlight that one because I'll get a circuit. So I got to say, oops, not allowed. So now I'm going to highlight some 5s. Here's a 5. Here's a 5. Here's a 5. Oops, and I can't do this 5 because that would make a circuit. Now, I want you to notice that if I put in a 6 here, I get a circuit. If I put in a 6 here, I get a circuit. If I put in a 6 here, I get a circuit. If I put in a 7 here, I get a circuit. There's nothing more to do. Everything is either highlighted and crossed out. And what we have discovered inside of this picture is our tree that lives inside of the graph. And this tree happens to be the best you can do. This works wonderfully. You actually get a known optimal answer. This algorithm, when you want to use weights associated with cost, edges need to be built, they're not there yet, and you want a tree, when you run this algorithm, which has a dead man's name attached to it, Kruskal's algorithm, this answer is optimal. And that's why it's got this guy's name attached to it, because it was an amazing fact that he came up with a way to guarantee the existence of this optimal solution. Now, there's a little bit more vocabulary associated with this subtree. We call it a minimal spanning tree. It's another common name, an MST problem. And the reason we call it this is, first off, the solution is a tree. Second, it is an optimal answer. It's the least cost. And the reason it's called spanning is that it is possible to get from every single point to every other point on this graph. Now, there could be more than one solution that could be picked. For example, our solution kind of looked like this. And there is one point that everything seems to be heavily dependent upon. And if you remember, when I was doing it, I had some choices of which to draw, which to pick rather than one and not the other. So it turns out that if you have a second choice, let's just pretend there was a second choice that looked like this. And let's suppose they were the same answer. I don't know if they were from the original problem. But I want you to notice that there is not quite the huge dependence on this one node here to get places. So there could be a human reason to pick this one over this one. That human reason is that we like the less dependence, or there's a lot of people that travel here and not so much that travel there, so we're not going to make to go from here to here through that extra point. In other words, if this is actually going to be used by humans, there's human reasons to pick one over the other. Almost every single time we do a problem and some human reason comes in to pick one over the other, we don't refer to it in math as a human reason usually. We just call it as an auxiliary condition. And the auxiliary condition here is we might pick a solution that has the least valence for the highest valence that's there. See, this one has a 1, 2, 3, 4, 5 valence. Now the highest valence in here is 4. So the highest valence in this picture is less than that one. So that could be an auxiliary condition that a human would pick one over the other. Now the beauty of having an algorithm that produces a unique answer is that we can ask the following question. Run an algorithm and tell us if you think it's optimal. And so let's just go over that the nearest neighbor. Don't know what kind of solution we know. We don't say not optimal. We say we don't know. Sorted edge algorithm. Don't know. Kruskal's. Yes, optimal. We have another algorithm called brute force, and that's when you draw every single one out. Yes, it's optimal because it will find it. But the problem with this is sometimes it can take 15,000 years to find. You can't wait for it. So we usually don't say that the brute force algorithm is an optimal algorithm for any answer, because we know that in general the brute force algorithm, it just doesn't finish frequently. It's true, it is a system by building a whole bunch of trees that you should find the right answer, but you won't necessarily find it in your lifetime. All right, now we're going to do a short diversion to a new type of graph. And this new graph is very common in our world. These new graphs that we're going to look like have arrows on them when you began. And we usually make the vertices large enough so we can put weights at the vertices, not on the edges. So this is going to be a new graph that is directed, no directed circuits. We can't go here, here, and we can't have one going back to there. That's not allowed. And it has weighted vertexes. So I'm going to put some numbers in here. 3, 2, 4, 2, 6, 1. And these weights usually are associated with cost, time, effort. And because it's most often used in terms of what's called tasking, we usually name the vertices with a very simple naming process. Task 1, Task 2, Task 3, Task 4, Task 5, Task 6. This directed graph represents a process of doing things. And the arrow means prerequisite. So this part of the picture right here says you can't do/start T2 until T1 is done. That's the requirement of the arrow. Now, these graphs can be disconnected, so I'm going to put a T7 and a T8 here of a 5 and a 4, and this is still a legitimate directed graph, no circuits with weighted vertices. And in fact, it's quite common. These graphs represent frequently jobs being done. So this might be, for example, building a foundation. This might be the permitting process. In other words, they are kind of independent of each other, but they can be done one when the other one is being done, or not done at the same time. Now, we do a couple of assumptions when we try to do this. We are going to schedule, and we're doing a couple things with the schedule. We're going to use people and machines, whichever you prefer. We could use robots or the like. And we have to pick the number. So we don't know how many people we're going to put on a job. That might be something we have to figure out. Sometimes we'll be given the number. And our goal is minimum time to completion. So if these are times, minimum time to completion, we may not be able to get it because this problem is fairly hard. The other thing is we can't put multiple people on a job. So each task gets one person. So if I put you on T1, I can't put anybody else on it. And now here's another thing. You always start and finish on time. So if I say you're going to start job T2 after Helen finishes T1 at 3 o'clock, you will start at 3 o'clock and you will finish at 5 because it takes exactly 2 hours. No worries about that. Also, you do one task a time. You can't split your work. So those are a couple of assumptions. We're going to try to schedule this. But the first thing we want to realize is that when we have a graph like this, it kind of would be nice to know what's the earliest, no matter how many people we have, we can get this done. What happens if we got to get this job done? Spacecraft's going to launch, or the road is going to open, or the army's going to invade, or the snow is coming and we've got to finish the road. I mean, there's a million reasons the jobs have to be completed, and you might want to throw more people at it to get it done. Well, I want you to notice, if you look at just this little bit right here, this says T7 must be done before T8, and then T8 can be done. It's a total job of these two things of 9 hours. So right now, you know, because of this single error in those two jobs, that it looks like 9 hours is maybe a minimum time to finish. It's got to be longer than that, but 9 could be the least. But now if I go up here and I look at this one, do T4, do T5, do T3, and then T6. Start here. Somebody does T4 after 4 hours. Somebody does T5 after 2 hours. Somebody does T6. We're assuming these were done. Somebody does T3 for 6 hours, then comes T6 for 1 hour. Well, there's 6, 12, 13. So one path was T7, T8, which was 9 hours. A second path was T4, T5, T3, T6, and we figured out that to be 12 hours. So now I ask you to find how many paths can you find here from a beginning to end? 1, 2, 3. Not too many. 5, 11, 13. Oh, 6, 12, 13. That was 13 hours. Sorry, I misadded. 4 and 2 is 6, 12, 13 hours. This path, 3, 2, 6, 1, is 12 hours. This T1, T2, T3, T6 is 12 hours. So this one right here, this very specific subpath within the picture says no matter how many people you throw at this big job, the earliest time you can finish this is in 13 hours. So what's strange is the longest subpath through the diagram is the quickest completion time. That has still an unknown number of workers, but the earliest this job could ever be done is in 13 hours. Now, finding critical paths is an important process because it helps us understand how to schedule. It turns out to be a critical analysis that we do. This is called critical path. And we put the word the in there. This guy right there is the critical path. There could be 3 that are equal. So then there's them, what's plural? Thuses, them, some, I'm not sure what the right word for many of critical paths, but they're all the same. There's a value that's unique. How long is a critical path? All right.